Hey folks, we're going to start up on our next lesson. I want you to have with you your Le Chatelier's principle notes page. That's how you pronounce it, Le Chatelier. If you didn't get that before spring break, you can download it in the spot right above. And you're going to need a writing utensil. So last time we talked about reversible reactions. Reactions where the reaction could go both left and go right. The things on the left side could react to form the things on the right, and the things on the right side could react to form the things on the left. And we also talked about the idea of equilibrium, the case where the reaction rate going right and the reaction rate going left are the same. And we noted there were several things that were true about that situation. Number one is that obviously the rates are the same going in both directions. It means that the concentrations of both two things stay the same as long as it's at equilibrium. It's just that the concentrations on both sides aren't the same. So you could have one that had a concentration of 10% and the other had a concentration of 30%, and those amounts will stay the same as long as it's at equilibrium. But the fact is that reversible reactions that are at equilibrium only stay at equilibrium when their conditions, and we mean by that concentration, temperature, and pressure, stay the same. So if a reaction is at equilibrium and we change the concentration, it will no longer be at equilibrium. The reaction rates going left or right are going to be bigger than the other one. It'll be out of balance, and it's no longer at equilibrium. And the same thing is true if we change the temperature, and the same thing is true if we change the pressure under certain circumstances. So that's our first idea. Now, we know that, as we said, the reactions equilibrium have the same reaction rate both left and right, but we change the conditions. And conditions, we're talking about concentration, temperature, and pressure. It'll no longer be at equilibrium, so a higher rate to the right or to the left. And it will do this until a new equilibrium is reached. So it may be that when you change the temperature that now the reaction rate to the right is bigger than the reaction rate to the left. But if the reaction rate to the right is bigger, then the concentration of the things on the right is going to rise. And it'll keep rising until we reach a new equilibrium. And then once that happens, the reaction rates are equal again. So we're going to go back to our stadium analogy. So we said before that we could have this reaction where basically people go from the stands into the restrooms, and they're going to keep, and at the beginning they're all going to flow into the restroom and no one's going to come out because no one's in here to start with. And so it's not at equilibrium. But eventually we reach a point where, let's say there are 50 people in the restroom and there are 9,950 people in the stands. And at that point, maybe the number of people that enter the restroom every minute is the same as the number of people who leave the restroom every minute. So let's say there are 10 people enter the restroom every minute and 10 people leave the restroom every minute. At that point, it's reached equilibrium. The number of people flowing in is the same as the number of people flowing out. And so the number of people in the restroom will stay the same even though they're not the same people. But let's imagine what would happen if we suddenly teleported 50 more people from the stadium into the restroom. Now we've changed the concentration of people. It's no longer going to be true that the number of people flowing in is going to be the same as the number of people flowing out, because a lot of those 50 people don't want to be in the restroom. Maybe some do, but most won't. And so for a short time, the reaction rate going out is bigger than the rate going in. There still are going to be 10 people trying to flow in, but there'll be 30 people flowing out. And those 30 people are going to flow out until we reach a new equilibrium. And the same thing might be true is what happens when the game's over. Let's say the game's over and 5,000 people leave the stadium. Well, when 5,000 people leave the stadium, at first, the number of people flowing out of the restroom is going to be still those 10 people flowing out to balance the 10 people flowing in. But now, with fewer people in the stadium, fewer people will enter the restroom. So now maybe 10 people are flowing out a minute, but only 5 people a minute are flowing in. That'll decrease the number of people in the restroom until it balances out again, until the 5 people flowing in is equal to the 5 people flowing out. And so that's sort of what happens when we change the conditions, is that the reaction rate flowing in and out, flowing left and right, will now be off equilibrium, will no longer be in equilibrium, and the reaction will shift until it reaches a new equilibrium. Now, we can predict how equilibrium will shift by using what's called Le Chatelier's principle. So French name, it looks like Le Chatelier or something, but it's pronounced Le Chatelier. And Le Chatelier's principle says this: if a chemical system at equilibrium experiences a change in concentration, temperature, or pressure, then the equilibrium shifts to counteract or undo the change and a new equilibrium is reached. The idea is that the reaction will always try to undo whatever change you made to it. If you increase the concentration, it's going to try to shift to decrease the concentration. If you increase the temperature, it's going to try to shift to undo to decrease the temperature. If you increase the pressure, it's going to shift to undo to decrease the pressure. So whatever you did to it, it's going to be out of equilibrium, and it's going to try to go and undo whatever you did to reach a new stable equilibrium. So let's go through how we figure that out. Step one. Let's say we change the concentration of a particular substance. Okay? Le Chatelier's principle says the reaction will shift to undo that change. So suppose we increase the concentration of CO2, carbon dioxide. Le Chatelier's principle says the reaction will shift to try to decrease the concentration of CO2. Okay, so since we increase CO2, Le Chatelier says the reactions will shift to decrease CO2, to undo what we did to it. We increased, it decreased it. What if we took away CO2? We decrease the concentration of CO2 in a reaction. Le Chatelier's principle wants to undo it, so it'll try to increase the concentration of CO2. So suppose we have this particular reversible reaction. We know it's reversible because we have the double arrows. H2O plus CO2 reacts in a reversible reaction to form H2CO3, which is called carbonic acid. So let's say that what we're going to do is that we're going to either increase CO2 or decrease CO2 or increase H2CO3 or decrease that. Once we know from the first step that if we increase CO2, Le Chatelier's wants to decrease CO2, or if we decrease H2CO3, Le Chatelier's wants to increase H2CO3. The second step is the reaction will shift either left or right in order to follow Le Chatelier's predicted change. Here's how we do it. Suppose we increase CO2. That means Le Chatelier's principle wants to decrease CO2. Well, how do we get rid of CO2? Well, to get rid of CO2, we'd want to break its bonds and make new bonds over here. So if we want to get rid of CO2 and move to H2CO3, this reaction is going to shift to the right. And so we would show that reaction as being one that would shift to the right. So if Le Chatelier says to decrease the concentration of CO2, the reaction would shift right. Okay, so what about our next possibility? So what if Le Chatelier's principle tries to increase the concentration of CO2? Well, now it wants to make more CO2, and since it wants to make more CO2, the reaction is going to shift toward the CO2, so the reaction would shift to the left. So last situation. What if Le Chatelier's principle wants to increase the concentration of H2CO3? Like we took away H2CO3 in step one, which means Le Chatelier's wants to undo it, so it's going to increase the concentration of this H2CO3. If it wants to make more H2CO3, that means it has to shift toward it. And so shifting toward it is going to be shifting to the right. So this reaction would shift to the right if it wants to increase the concentration of H2CO3. And that's how we do step two. Final step. Use the direction of the shift to find what happens. So let's say the reaction shifts to the right. So if the reaction, according to Le Chatelier's principle, wants to shift to the right in response to whatever we did to it, then it means the amount of H2CO3, the concentration of H2CO3, would have to increase because we're moving toward it. We're making more of it. What would happen to the concentration of H2O if the reaction shifts right? It would go down because we're getting rid of it. We're breaking its bonds in order to make more of the H2CO3. And so we can see that. If the reaction shifts right, the concentration of H2CO3 increases because we're moving toward it, making more of it. If the reaction shifts right, the concentration of H2O decreases because we're taking it apart. We're shifting away from it. On the other hand, if the reaction shifts left, then it's going to be moving this way, according to Le Chatelier's principle. is we're going away from the H2CO3. We're getting rid of it. We're taking it apart to make more of the stuff that's on the left. So that means the concentration of H2CO3 decreases. So reaction shifts left, the H2CO3 decreases. What about the H2O? The reaction shifts left, the concentration of the H2O should increase because we're shifting toward it. We're making more of it. So let's go through all the steps. I have this reversible reaction, N2 plus 3H2 yields in a reversible reaction to NH3. So step one, what are we doing to this? Well, let's say we increase the concentration of H2. We add more H2 to this thing, increasing its concentration. Step one says Le Chatelier's principle always wants to undo the change we made. So Le Chatelier says the reaction will shift in response to undo the change. So since we increased H2, it's going to decrease the concentration of H2. That's step one. It's going to want to decrease the concentration of H2. So I usually like to do this by drawing a little arrow down here to remind myself it's going to decrease the concentration of H2 in response. So if it wants to decrease the concentration of H2, that means the reaction has to shift away from the H2. So the reaction in response is going to shift to the right, to go away from the H2. Okay? So that's our second step. So to decrease concentration of H2, the reaction will shift away to the right. If the reaction shifts to the right, what's going to happen to the amount of NH3? Well, the amount of NH3 should go up because we're shifting towards it. So the amount of NH3 should go up in response, and the concentration of N2 should go down in response. So the reaction shifts to the right, the concentration of NH3 will increase because we're shifting toward it, and the concentration of N2 will decrease because we're shifting away from it. And that's how you want to talk through and work through a Le Chatelier's problem. First, what do? We increase the concentration of H2. Second, what does Le Chatelier's principle say? It wants to undo the change we made. Since we increased H2, it wants to decrease H2. Next, which direction does that make the reaction go? To decrease H2, it wants to shift away, which is to the right. And then lastly, if it shifts to the right, what happens to the other guys? If it shifts to the right, we're going away from the N2, so N2's concentration drops, H2's concentration drops, and NH3's concentration rises. And that's how we work out a Le Chatelier's problem. So let's try another one. So N2 plus 3H2 yields 2NH3. We start off by decreasing the concentration of H2. We take away H2. So if we decrease the concentration of H2, Le Chatelier's principle says the reaction will shift to undo our change, to increase H2. So Le Chatelier's is going to try to increase H2 in response. So I'll draw an arrow to indicate that in response, H2 increases. To increase the concentration of H2, that should be the word increase right there. To increase the concentration of H2, the reaction has to shift toward the H2, which means it shifts towards the left. So I'm going to draw an arrow up here to show the reaction shifts toward the left. If the reaction shifts towards the left, then that means it's going away from the NH3. That means the concentration of the NH3 is going to go down, and the concentration of the N2 is going to go up. So if I had this reaction at equilibrium and I got rid of H2, what I would find is I'd find it's going to make more N2 and it's going to make less NH3. Second thing that affected Le Chatelier's principle was temperature, or affected a reaction equilibrium is temperature. So first thing, one thing we want to notice is that this particular reaction, the way we've always talked about it, should be an exothermic reaction. We notice the chemical energy drops, and since the total energy stays the same, that means the thermal energy goes up. But that's only true if we go from left to right, which is the way we normally do chemical reactions. But what if this reaction is reversible? We can go from right to left. Well, if we go from right to left, the chemical energy rises, which means the thermal energy falls, and this reaction is endothermic. So we would say this reaction is exothermic going to the right, but endothermic going to the left. Just as a rule, If we ever just need to say for a reversible reaction, whether it's exothermic or endothermic, we're going to say like it's if we just say this reaction is exothermic, we mean it's exothermic when it goes to the right. If we say this reaction is endothermic, then we mean it's endothermic when going to the right. So if we just said this particular reaction is exothermic, we mean exothermic going to the right, but endothermic going to the left, just so you know about the convention. So let's say that we have a mixture of this H2 and O2 and H2O, and it's in a pot, and it's all reacting, and it's a reversible reaction. So H2 and O2 react to become H2O, and H2O splits apart and breaks its bonds and becomes H2 and O2, and it's reversible. And we leave it alone until it gets to equilibrium, and it's at a nice equilibrium, and we heat it up. Well, we know this. If we heat it up, then Le Chatelier's principle says it wants to undo that. So it wants to cool down. And so that means the reaction will shift to the cooler side, to the more endothermic side. So which side of these is going to be the cooler side? Well, the cooler side is the side with less thermal energy. That's going to be the left side. So this reaction would shift left, which would then mean the concentration of H2O would go down, the concentration of O2 would go up, and the concentration of H2 would go up. So let's say that we have this reaction, and now we're going to cool it down. So if we cool this reaction down, Le Chatelier's principle says it's going to respond by trying to heat up. So if it wants to heat up, it's going to go to the warmer side. Well, which side's the warmer side? The warmer side should be the more exothermic side, the one with more thermal energy. So this would be the hot side right over here, and then this right over here would be the cold side. All right. And so since we cooled it down, Le Chatelier's wants to warm it up. So it's going to shift to the warmer side, which means shift towards the hotter side. It'll shift right. And so if the reaction shifts right, that means we're going to increase the concentration of H2O in response, and it will decrease the concentration of these two guys, of the H2 and the O2 in response. So by cooling this down, we would end up making more H2O and making less H2 and less O2. So let's try another one out. So it tells us this is an exothermic reaction at equilibrium. N2 plus 3H2 yields in a reversible reaction, 2NH3. First thing I always like to do is when I'm dealing with a temperature one, because it says we increase the temperature, is label the warm side and label the cold side. It tells us this is an exothermic reaction. And remember, that means it's exothermic when going to the right. So if we go to the right, it's going to get warmer. So I'm going to say that this side over here is going to be the hot side, and the left side will be the cold side. So I'm going to do that before I even start the problem, just to make sure I understand what's going on. So we increase the temperature. Le Chatelier's principle says it's going to try to respond by undoing our change, so it will try to decrease the temperature. If it wants to decrease the temperature, the reaction will shift towards the endothermic or cooler side, which is the left side. So that means this reaction is going to shift left. So I'll draw my arrow to show that it's going to shift left. If the reaction shifts left, then that means that the concentration of N2 will go up because we're going toward it, of H2 will go up because we're going toward it, making more of it, but the concentration of NH3 will go down because we're shifting away from it. So we know that if we heated up this reaction, we would end up with a higher concentration of N2, we know we would end up with a higher concentration of H2, and we would end up with a lower concentration of NH3. So let's suppose that we've got one like this. An exothermic reaction at equilibrium. So since it's exothermic, we know that means exothermic when going to the right. And so if it's exothermic going to the right, that means that the side on the right is the warmer side, and the side that's on the left is going to be the cooler side. So I like labeling those first. So what do? We decrease the temperature. So Le Chatelier's principle wants to get it back into an equilibrium, so it's going to try to undo what we did, so it's going to try to increase the temperature. If it's going to try to increase the temperature, it's going to go towards the warmer side. So the warmer side is going to be over here, so this reaction will shift to the right. So as it says, to increase the temperature, the reaction will shift to the exothermic side, to the right. If it shifts to the right, what's going to happen? Well, if it shifts to the right, then the concentration of NH3 is going to go up because it's shifting toward it, making more of it. the concentration of N2 will go down because we're shifting away from it, and the concentration of H2 will go down. So as it says, if the reaction shifts to the right, concentration of NH3 will increase, and the concentration of N2 and H2 will decrease. So one more on this. Suppose we have an endothermic reaction at equilibrium. H2CO3 yields in a reversible reaction, H2O plus CO2. First step, since it says we're decreasing the temperature, let's figure out which side's the warmer side and which side's the colder side. So it tells us this is an endothermic reaction. That means as it goes to the right, it gets cooler. If it gets cooler as it goes to the right, that means that this side is the warmer side because the other side has to be the cooler side. So I'm going to label those first. Once I know that, I can start working through my Le Chateliers. So if we decrease the temperature, Le Chateliers is going to respond by trying to increase the temperature. It's going to shift towards the warmer side. And so the warmer side here is going to be the left, so this reaction will shift left in response. If it shifts left, that's going to increase the concentration of H2CO3, and it's going to decrease the concentration of H2O and of CO2. So if we cool down this particular reaction here, what we would find out is the concentration of H2CO3 would go up, but we'd end up with less H2O and less CO2. Next one we're going to talk about is about pressure. Now what's important to know about pressure is that pressure only affects the equilibrium of a reversible reaction if all of the substances are gases. Not almost all, every last one. If not all of the substances are gases, pressure does not affect the equilibrium. Changing the pressure will not shift anything at all. When we talk about gases, the reason why that we only want to talk about gas pressure is gases cause pressure due to impacts of the particles against the walls. So here we have two gases. We have red gas and we have blue gas. And so if you think about it, each of these particles in a gas is not held together. They're all flying around at every which way. They've been able to escape from their intermolecular forces for the most part. And these particles are constantly running against the walls. And so if you think about it, the blue gas is going to hit the wall a lot. And so it's going to put a big pressure because there are lots of blue particles hitting the wall. Red gas, on the other hand, there are a lot fewer particles, so they're going to hit the wall a lot less often. And so gas pressure is caused by the impact of the particles on the wall. In this case, because there are more blue particles, the blue gas will exert a higher pressure on the wall, and the red gas will exert a smaller, lower pressure on the wall. So to summarize, the more particles of a gas that hit the walls, the higher the pressure. So let's assume we have this particular reaction. So N2 plus 3H2 yields 2NH3. So let's imagine that this reaction was 100% on the right side. It had gone all the way over the right, nothing left on the left. Since it's 2 NH3s, there would only be two particles there. But let's imagine the reaction was 100% the other way. It was all on the left and there was none on the right. Well, over here, there's 1 NH2 plus 3 H2 for a total of 4 particles. So when this reaction was, if this reaction was entirely on the right, there would be 2 particles. If it were entirely on the left, there would be 4 particles. What this means is that the more this reaction shifts to the right, the fewer particles there will be, which means the pressure will decrease. Because remember, fewer particles means fewer impacts, which means lower pressure. But if this reaction shifts to the left, there'll be more particles, which means there are more things hitting the wall, which means the pressure will increase. So we know this. Shifting towards the sides with more particles increases the pressure. And we find whether there are more particles by sort of counting up the coefficients on each side. We don't care about the little 3s or the little 2s down here. They're just reach the most stable state as far as the electrons go. But here we just say 1 N2 plus 3 H2s gives us a total of 4 particles. Here we just have 2 NH3s for 2 particles. Shifting to the right decreases the pressure. Shifting to the left would increase the pressure. So a couple things we need to remember about Le Chatelier's principle. As we said before, if any one of the substances is not a gas, changing the pressure will not shift the equilibrium. So that means there's no change. So if we were to increase the pressure, but one of them was a liquid, it wouldn't change, it wouldn't shift left or right, nothing would happen. If we had the same number of particles on both sides, let's say there were 3 particles on the left and 3 particles on the right, then changing the pressure has no effect. It wouldn't shift anything. Le Chatelier's principle doesn't do anything. So let's try one out. In a reaction of all gases at equilibrium, N2 plus 3H2 yields 2NH3. We increase the pressure. Anytime you have a pressure question, you're going to start off by writing out how many particles are on both sides. So here I have 1 particle of N2 and 3 of H2 for a total of 4 particles. And here I have 2NH3 for a total of 2 particles. So all right, so I now know how many particles I have on each side. Next thing I want to check, are they all gases? Yes, all gases. So now let's just go through the Le Chatelier steps. We increase the pressure. If we increase the pressure, Le Chatelier's is going to try to undo that to decrease the pressure. So Le Chatelier's wants to decrease the pressure. So to decrease the pressure, it wants to shift to the side that has fewer particles. So that means it will shift to the right, because that would take it from 4 particles to 2 particles. So this reaction would shift to the right in response. If it shifts to the right, then the amount of NH3, the concentration of NH3 will go up, and the concentration of N2 will go down, and the concentration of H2 will go down. And so that means for this particular reaction of all gases, if we increase the pressure, we pressurize it, then we're going to end up with more NH3 and less N2 and less H2. So similar situation. Since we're changing the pressure, we're going to go ahead and write out how many particles on both sides. We know this one is 4 because it's 1 plus 3, and this one is 2 because we've already seen that right there. So we decrease the pressure. If we decrease the pressure, Le Chatelier's is going to cause the reaction to shift to undo our change, to increase the pressure. If it wants to increase the pressure, it's going to shift to the side that has more particles. And more particles 4 versus 2, so it'll shift towards the more particle side. If it shifts to get more particles, then it's going to increase the concentrations of the things on the left, because we're going toward the N2, making more N2. We're going toward the H2, making more H2. And it means we're going to go away from the NH3, so its concentration would drop. So if we decrease the pressure, that would result in more N2 being produced, more H2 being produced, but we'd end up with a lower concentration of NH3. So one of the reasons why we care about using Le Chatelier's principle is that there are times when we have reversible reactions that are used like in a process where we're actually trying to make something. So let's take this particular reaction. N2 plus 3H2 yields 2NH3. N2 is nitrogen gas. It makes up, 78% of our air. And so it is super cheap. And so you can get it really easily. H2 is hydrogen gas. While it's not as easy to make as nitrogen, really all you have to do is take water and run electricity through it, and that'll make H2. Since water's cheap, electricity's cheap, H2 is cheap. On the other hand, NH3 is ammonia. We use it sometimes in our fields as anhydrous ammonia. It's a little more expensive. And so if you have this reaction, really you can take 2 cheap things and use it to make something that's more expensive. And if that's true, that means you can sell it and you can make money. And so oftentimes is that what we want to do in chemical reactions is we want to shift the equilibrium to increase the amount of the more valuable thing. We want to shift this reaction to the right to make more NH3 and make more of the cheaper things. So that way we can add cheap things and it'll make more of the more expensive thing. So let's say our goal is to make as much as possible of this valuable NH3. So let's say we know a few things. N2, H2, and NH3 are all gases, and this reaction is exothermic, which remember means it's exothermic going to the right. So let's go ahead and start off by adding in the things that we know are true. So since they're all gases, then we're going to put the number of particles. So there's 1 nitrogen and 3 hydrogens for a total of 4 particles on this side. 2 NH3s for a total of 2 particles on this side. It tells us the reaction is exothermic, which means the right side is going to be the hotter side, and the left side is going to be the cooler side. Okay, it is a reversible reaction. Our goal is to make as much as possible of the valuable NH3. That means we want this reaction to shift toward the NH3. So that means this reaction is going to shift right. So let's see, how could we make the reaction shift right? Well, concentration-wise, if we want this reaction to go right, we want to add into an H2. Why? Because if we add into and add H2, the reaction will try to undo adding these, so it'll try to go away from them. It'll shift right, which will make more NH3. So one way to produce more of the valuable NH3 is to add more cheap N2, add more cheap H2. That'll make more of the nice expensive NH3. The second thing that we could do is we could remove NH3. As soon as it makes NH3, we take it out immediately. Here's why. Because if we take out the NH3, we're decreasing the concentration of NH3, which means Le Chatelier's will try to increase the concentration of NH3. How does it increase it? By shifting toward it, shifting to the right. And so it'll then make more NH3. So for every bit we take out, the reaction shifts to try to make more of it. And so decreasing our concentration of NH3 would also end up making more of our valuable NH3 from our cheap N2 and cheap H2. Temperature. Well, if we want this reaction to shift right, we want it to shift towards the warm side, towards the hot side. Well, how do we get Le Chatelier's to get hot? Well, we cool it down. If we decrease the temperature, Le Chatelier's principle will try to undo that change by increasing the temperature, shifting towards the hot side, which is the NH3, which will make more NH3. So if we have this reaction going on, we want to cool it down as much as possible, as long as these things all stay a gas, because if they're not gases, we can't use pressure. So we decrease the temperature until as much as we can to shift this reaction to the right. Last one we want to do is we want to increase the pressure. Why would increasing the pressure work? Well, if we increase the pressure, Le Chatelier's principle wants to decrease the pressure, so it'll shift to the side with fewer particles, which is the right. And if it shifts to the side with fewer particles, it's going to make more of the valuable NH3. And so this is a way that we can use Le Chatelier's principle to make more of something we want and make less of something that we don't want.